Hey you, I have a question. What do a floating ship, a soaring airplane, and a simple hydraulic jack all have in common? They all operate because of the incredible power of fluid mechanics. And today, right here, we're going to unravel its secrets, from the pressure principles of Pascal to the floating magic of Archimedes, all the way to the force of flight explained by Bernoulli. This is Fluid Mechanics, and you're about to see it in action. So, what is fluid mechanics? It is the science of how fluids, like liquids and gases, move and behave. Moreover, it's the hidden set of rules that explains why water flows, why air lifts a plane, and why we can float. It's the powerful physics behind everything from the swimming pool to a rushing river to a hurricane. Now, let's dive into the wonders of fluid mechanics.
Let's start with Pascal's principle. It states that pressure applied to an enclosed fluid is transmitted equally throughout. In equation form, F sub 1 over A sub 1 equals F sub 2 over A sub 2. So watch this underwater demo. When I squeeze this bottle underwater, you can see the pressure transmitted throughout the bottle.
Now, let's take a deeper dive into one of the most powerful applications of Pascal's principle, hydraulic system. So, what exactly is hydraulic system? In simple terms, it's a force multiplying technology that uses an enclosed incompressible fluid like oil or water to transfer energy from one place to another. Key components are: number 1, a fluid, the magic messenger that transmits the pressure. Number 2, two pistons, a small one for input and a large one for output. Number 3, a connecting tube, the path the fluid travels through. The hydraulic lift is Pascal's principle in action. Think about a mechanic lifting a car. Impossible for one person, right? But with hydraulics, it's easy. How it works is that a small force on a small piston creates pressure that gets transmitted to a large piston. Since pressure equals force divided by area, and the pressure is equal on both sides. If the large piston's area is 50 times bigger, the output force is 50 times stronger. That's force multiplication. A hydraulic jack is just a portable hydraulic lift. Same science, same amazing results with minimal effort. Let's solve a quick problem. A hydraulic lift has a small piston with area 2 cm squared and a large piston with area 50 cm squared. If I apply 100 N of force to the small piston, how much weight can the large piston lift? Given that A sub 1 equals 2 cm squared, A sub 2 equals 50 cm squared, and F sub 1 equals to 100 N, we can now solve for F sub 2. Using Pascal's principle, F sub 1 over A sub 1 equals F sub 2 over A sub 2. We can write the problem as F sub 2 equals 100 newtons times 50 over 2, which equals to 100 newtons times 25, and then leads to our final answer, 2,500 newtons. So with just 100 newtons of force, I can lift 2,500 newtons. That's 25 times more force. That's the power of hydraulics.
Now let's get wet with Archimedes' principle. The buoyant force equals the weight of the fluid displaced.
F sub beta equals W sub FL, or F sub beta equals density times volume times gravitational acceleration. When I lift my friend in water, she feels lighter. That's buoyant force. Let me show you the forces on an object in water using a free body diagram. For any submerged object, there are two main forces: weight, W sub FL, pulling down due to gravity, and buoyant force, F sub beta, pushing up from the water. The net force determines what happens. If F sub beta is greater than weight, then the object floats upward. If F sub beta is less than weight, then the object sinks downward. And if F sub beta is equals to weight, then the object stays suspended. Now let's solve a quick problem. A 2 kilogram object with volume 0.003 cubic meters is completely submerged in water. Density equals 1000 kilograms per cubic meter. Will it sink or float? Given that m equals 2 kilograms equals 9.8 meters per second squared, v equals 0.003 cubic meters, and the density of water is 1000 kilograms per cubic meter. We must first calculate the weight, where W equals m times g. Substituting the values, W equals 2 kilograms times 9.8 meters per second squared. Therefore, W equals 19.6 newtons. Now, the buoyant force equals the weight of the displaced water. F sub beta equals rho of water times volume times gravity. Substituting the values, 1000 kilograms per cubic meter times 0.003 cubic meters times 9.8 meters per second squared. Therefore, F sub beta equals 29.4 newtons. Since F sub beta, which is 29.4 newtons, is greater than the weight, which is 19.6 newtons, the object will float upward. The buoyant force wins.
So I have a question. Why do some things float and others sink? Well, it's all about density. So for our experiment, let us try these three things to know if it will sink or if it will float. First is a plastic bottle. Oh, it floats. Since it has a low density and even some air inside it, it can help it stay on top. Next is an apple. As we can see, it mostly floats because its density is just less than of a water and its tiny air pockets will help it float. Last item is a rock. Oh no! It sinks! Since it has a low density, it will go straight to the bottom.
Now, let's talk about fraction submerged. The fraction of an object that's underwater equals its density divided by water's density. If your density is 800 kg per cubic meter and water is 1000 kg per cubic meter, then 800 divided by 1000 would be 0.8, so 80% of you is submerged. Now, we will talk about specific gravity. Specific gravity is just density compared to water. It's a simple number that tells you everything. Less than 1 means you float, more than 1 means you sink, and exactly 1 means you hover.
So now, let's see Archimedes' principle in action.
When we swim, we displace water, creating buoyancy. More surface area equals more buoyancy. Watch this ball blast up when I release it underwater. That explosive force is the buoyant force, way stronger than the ball's weight thanks to Archimedes' principle. To understand flowing fluids, we first need to know about ideal fluids. These are fluids that are non-turbulent flows. Turbulent flows is a regular flow characterized by small whirlpool-like regions. Steady-state flow. In steady-state flow, the velocity of the fluid at each point remains constant. Non-viscous fluid. Internal friction is neglected and object moving through the fluid experiences no viscous force. Incompressible fluids. Density is constant throughout the fluid. Now, for the continuity equation, where it's all about conversion of mass. Equation form, A sub 1 over V sub 1 equals to A sub 2 over V sub 2. What flow is a mass flow out? If a pipe gets narrower, the fluid has to speed up to keep the same flow rate. Watch! When I partially block the hose opening, the water shoots out faster. Same water, smaller area equals higher speed. Let's solve this. A pipe with 30 cm squared area has water flowing at 2 meter per second. It connects to a narrower pipe of 10 cm squared. What's the speed in the narrower section? Given A sub 1 as 30 cm squared, V sub 1 as 2 meter per second, and A squared as 10 cm squared, you can use the continuity equation to solve for V2, where 30 cm squared times 2 meter per second is equals to 10 cm squared times V sub 2 equals to 60 equals to 10 times V2, then V2 equals to 6 meter per second. Therefore, the water speeds up to 6 meter per second in the narrower section. That's 3 times faster.
Now, for my favorite, Bernoulli's principle, where fast-moving fluids have lower pressure. Bernoulli's principle is all about conservation of energy. In equation form, pressure sub 1 plus 1/2 times density times fluid velocity sub 1 squared plus density times gravity times h sub 1 is equals to pressure sub 2 plus 1/2 times density times fluid velocity sub 2 squared plus density times gravity times h sub 2. The equation looks complex, but the idea is simple. It says that in a flowing fluid, you have 3 types of energy. First one is pressure energy. Second one is kinetic energy, which is 1/2 times density times fluid velocity squared. And lastly, potential energy, which is density times gravity times height. And the total always stay the same. This equation shows the trade-off. When fluid speed increases, pressure decreases. Let's have some poolside and pool demonstrations. Bernoulli's principle is what makes this paper airplane and a real airplane fly. The wing is shaped so that air has to travel faster over the curved top than the bottom. Watch these 2 balloons when I blow air between them. They don't push apart, they pull together. The fast-moving air creates lower pressure between them, and the higher pressure on the outside pushes them together. That's Bernoulli's principle in action. Now, let's have an example. Water flows in a ground-level pipe at 2 meters per second with pressure 5,000 Pascal. The pipe then narrows, rises 3 meters, and the water speeds up to 5 meters per second. What's the new pressure? Suppose the density of water is 1,000 kg per cubic meter. Given that V sub 1 is 2 meters per second, V sub 2 is 5 meters per second. H sub 1 is 0 since it is in ground level. H sub 2 is 3 meters. Density is 1,000 kilograms per cubic meter. Gravity is 9.8 meters per second squared. And P sub 1, which is 50,000 Pascal. We can now solve for P sub 2. Using Bernoulli's principle, we must first solve the kinetic energy and potential energy from both sides. For the first kinetic energy, we have 1/2 times 1,000 times 4, which is 2,000 joules. For the second kinetic energy, we have 1/2 times 1,000 times 75, which is 12,500 joules. For the first potential energy, we have 1,000 times 9.8 times 0, which is 0 joules. And for the second potential energy, we have 1,000 times 9.8 times 3, which is 29,400 joules. Now, let's solve for P sub 2 by using Bernoulli's principle and transposing the relevant variables to the other side, which leads to P sub 2 is equals to 5,000 plus 2,000 minus 12,500 minus 29,400, which P sub 2 is equals to 10,100 Pascal. See the drop? The pressure fell dramatically because the water both sped up and gained height. That's why water pressure decreases on higher floors. Bernoulli's principle explains it all. Let's review the demonstrations in this pool we have seen.
Pascal's principle in hydraulic systems.
Archimedes' principle keeping us afloat.
Density determines which floats or sinks.
continuity equation in water flow.
And Bernoulli's principle in both air and water. So you see, from the cars we drive, to the planes in the sky, from the water we drink, and to the pools we swim in, all we can say is that
Fluid mechanics is everywhere!
Thank you for watching. See you next time.